Hey, Algebra 2, we're in section 7.7 and we're going to be talking about operations on functions. So we have one vocabulary word that is composition of functions, or phrase, I should say, that's composition of functions. And basically what this means, you know what functions are, right? You might have like a little f of x is equal to 3x plus 5. And you remember how we deal with them. Like you might be asked, what is f of 3? And so you know that wherever the x is, you're going to put the 3. So 3 times 3 plus 5. And then you would get that that answer is 14. And you could also like evaluate weird things like f of r. And you would just replace the x with r and you'd get this. Or even f of can, right? Doesn't matter. You're just literally replacing the x value with whatever you are told to. And so sometimes we might have f of g of x. Okay, so remember how we just replaced everything in our function with whatever was inside this. Sometimes I call it a kangaroo pouch because I'm that kind of person. So everything that's in this like little kangaroo pouch, right? You replace it in the function. So that's what we would do here. But in this case, we would be given a value of g of x. Let's say g of x is equal to x squared. So now instead of plugging in a number or plugging in a weird variable or some word, you're plugging in an expression. And so f of g of x is the same as f of x squared. And remember the function is 3 times x. We're going to replace that with x squared. So 3 times x squared plus 5. This is what we call a composite function, where you take two functions, two or more functions, and you morph them into each other, not by adding, subtracting, or multiplying or dividing, which we're going to talk about today, but where you literally tuck one into the other. And by the way, if I did it the other way, g of f of x, because I know you were wondering, you're like, well, wait a minute, what if we did it the other way? Will we get the same answer? And the answer is most times no. G of f of x would be me taking the f of x function and plugging it into the g of x function. Remember, the g of x function just says take the x and square it. So we're going to take f of x, the whole function f of x, and square that. That's what we're asked to do here, because the outer function is the one that we're which kind of gives us the framework. So f of x, quantity squared, and remember f of x is 3x plus 5. So that'll be 3x plus 5 quantity squared. And we're big timers now. We know how to multiply that. That's 3x plus 5 times 3x plus 5. And what that's going to give us is the following. We're going to end up with 9x squared with a 25 back here and a plus 30x in the center. And so it's a perfect square trinomial. So let's just look at it real quick. When I take composite functions, when I do f of g of x, I can write it like this. There's another way to write. We'll look at that in a minute. I'm going to get 3x squared plus 5. When I take g of f of x, I end up with 9x squared plus 30x plus 25. A very different answer. So don't think that you can do it either way. The other way that you might see this written, and it looks close to the multiplication, you might see it as g of this f of g. These two means the same thing. It means f of g of x, but it looks like fog. And then g of f of x, it looks like golf. But it's really the same thing as the other values. So you'd get the same value no matter what way you do it. I actually prefer this functional notation than this one, but I would just want you to be prepared. So that's the only new concept of this chapter. Let's get started with some of the questions. So here we are. We're given that f of x is equal to this particular value, x squared minus 3x plus 1, and g of x is equal to this, 4x plus 5. They asked us to find the sum of the two functions. So basically, this is pretty fun. We know that this really just means add the two functions together. Just do that. So what is f of x? It's this business here. And what is g of x? It's this business here. We're going to add them up and we're going to join like terms together and we'll get our answer. So when I bring these two functions together, I'm left with x squared plus x, right? Because these guys came together to give me 1x, and then plus 6. And that's what we got. Cool? Hopefully that makes sense. I hope it makes sense. All right, so we're going to do the same thing here, except this time they're asking us to subtract. And I think you've got the hang of it already, right? F of x minus g of x is what they're asking me to calculate there. What's f of x? We remember. And what's g of x? Given to us right there. What I would do in this scenario, though, is I will put parentheses. Those parentheses are really important. I will put parentheses around the whole thing that I'm subtracting, and that will remind you that you have to do a little bit of a distributive property here. So this is really x squared minus 3x plus 1 minus 4x minus 5. And so we're going to join like terms together, and we'll get x squared minus 7x minus 4, because I bring these guys together and I get a 4. All right? All right, so we are creating new functions by taking two functions and performing operations on them. So another pair of operations that we can perform is multiplication and division, as you see here. So just like you suspect, f times g of x, not to be confused with the composite function, the fog and the golf business, or the f of g of x and the g of f of x business, but this really does mean multiplication. So we're going to take f of x and we're going to multiply that by g of x. Here f of x is x squared plus 5x minus 1. And g of x is 3x minus 2. And we're going to use the extended distributive property, where we just kind of extend and we take each of these terms and we multiply into the next expression. So x squared times 3x is 3x to the third power. X squared times the other one is a negative 2x squared. Now for the 5x times 3x is going to be a positive 15x squared. And then 5x times a negative 2 is a negative 10x. Multiply everything by negative 1, I get a negative 3x and a plus 2. I'm going to join some like terms together if I can. 3x cubed is a loner, and I've got a couple of x squareds, which is going to give me a plus 13x squared. These guys come together to give me a minus 13x, and this is going to be left here plus 2. So this is what these two functions multiplied look like. When I have division, I'm going to do a similar thing. It's going to be, in this case, f of x over g of x. And I'm going to put x squared plus 5x minus 1, 5x minus 1, all of that over 3x minus 2. And now that I've done that, I have this new function. One of the things that we should probably start to think about is, like, what's the domain? What values make sense here? Like, I can put any number in the top. It doesn't really matter. But the denominator, there's a number that I cannot substitute in here. This function is all good, but the domain is very specific. The domain is all reals except what's going to make this denominator 0, right? And so if I set that denominator equal to 0, I get 3x is equal to 2, and therefore x is equal to 2/3. Domain is all reals except for 2/3. Why? Because now when we have a fractional expression, we need to consider what values are going to make sense. And the only values that make sense are numbers that are not going to give me a 0 in the denominator. You see that? So now you'll start to see every once in a while, kind of like, I kind of call it like a like the fine print, right? Here, this is the function, but remember, 2/3 can't work in the denominator. And so the domain is everything except for 2/3. All right, so we're going to evaluate composition of relations. So f of x is now, we're not given an equation, but we're given literally a relation here. 7, 8, and 5, 3 are all elements of the f of x function, and the g of x function has the ones that you see before you. So what we'll do now is figure out, find f of g of x and find g of f of x. So let's take our time. So f of g of x, or when it's written like this, we know that's f of g of x. And we'll find that value, and we'll write those values. And g of f of x, we'll find these values. G of f of x. Okay. So the thing about this function is that you do what's on the inside first, and then you use the outside function as your guide. The outside function is like the template for the whole thing, but the inside function is where you start. So if I want to look at this first value, when I plug 5 into g of x, I would get 7. So what is f of 7? F of 7 is going to be 8. So watch this. F of g, well, I am not going to write it like that. I'm going to write it like this. When I plug 5 into this composite function, I don't get 7, I get 8 because it has to go through the g and then through the f function. I hope that makes sense. So 5, 8 is 1 point. Let's do this one. When I plug 3 into the g function, I would get 5 as an answer. But now when I plug 5 into the f function, I get 3 as an answer. So the ordered pair here would be 3, 3. Let's look at this next one. If I plug 7 into the function for g, I get 9 as an answer, 9 as a result. But when I plug 9 into the f of x function, I get 8. So 7, 8 is the value that I have here. 7 in and then 8 out. Again, if I plug in 9 into the g function, I'm going to get 11. Now, if I plug 11 into the f function, I get 4. So the composite is going to be 9, 4. So this composite function, f of g of x, is going to give me the following values. Let's do it the other way. If I plug, say 7 first into the f of x function, I'm going to get 8. But then when I plug 8 into the g of x function, I can't do it because there's no 8 value there, right? There's no 8 that is a part of the domain. So when f of x is 7 and we get that 8 and 8 doesn't actually work out, we say that the function is undefined, right? It's undefined at 7. At 7. All right, so let's look at the next value we can try. We're going to plug in 5 into the function, and when I plug 5 in, I get 3, and so I look over here. When I plug 3 in, I get 5. So that is a point. When I plug 5 in, I get 3, and then when I plug 3 in, I get 5. So 5, 5 is a point that is in this function or this composition g of f of x. Let's do another one. I'm going again first to the f of x term, so I'm going to 9. And when I plug 9 in, I get 8 for f of x. And if I do 8, oh, wait a minute, I'm running into the same problem. So again, it is undefined. This new created function is undefined at 9 because 8 is not a part of the g's domain, right? Let's try one more. And finally, if we plug in 11 into this function, we get 4, and we try 4, and we see we don't have it because 4 is not a part of the domain of g. So I end up with an undefined also at 4. At 4? At 11. I'm going to change that to 11 there. Okay, good. So this is what we have. Just because a function works in one direction doesn't mean that you're going to, or a composition works in one direction doesn't necessarily mean that the composition will be, work in the other direction, particularly because of the limitations of the domain. And so let's look at this simplified composition of functions. So this is more like what we talked about earlier on. We've got g of f of x and f of g of x and g of f of x for the following. And so I'm going to write f of g of x like this. Again, I told you it's just my preference. And then I'm going to handle that. So the first thing I do is I'm going to take the g of x function and plug it in for the f of x function, which gives us our framework. So g of x is shoved in here, and so we get x squared plus x minus 1. That's g of x plus 3, because g of x is plugged in for the x. And then if I simplify that, I get x squared plus x plus 2. And that's my composition f of g of x. Let's do it the other way, g of f of x. And g of f of x is basically me just rewriting that one. And so when I do that, I now start off with the f of x. What is f of x? F of x is x plus 3. What am I going to do? I'm going to shove it in for all of the x values in the g of x, because g of x is now giving me the template, the structure. So I write out my structure like this, and I'm going to substitute x plus 3. After that, I'm going to simplify each section by squaring and joining like terms. and I get this as my final answer.